Before heading to the video, if you haven't subscribed the channel, do subscribe it and don't forget to click the bell icon for the latest update notification. If you like the video, do like, comment and share. Stay tuned with learnbay.co. Happy learning!
Okay, so what happened is now TensorFlow 2 came, I think, in this last year. So TensorFlow 2 came like literally last year. And so there is a significant difference in TensorFlow 1 and TensorFlow 2 variants. Okay, so what I've decided is to kind of use a different code or altogether. I would actually use much different code earlier, but I'm looking into a very different code altogether so that you guys are updated with the latest knowledge how to make TensorFlow work. So earlier the scenario was like this. So there was TensorFlow, okay, and so TensorFlow you could design almost the whole neural network in TensorFlow if you wanted to. Now from moment of TensorFlow 2.0, it has been like this that TensorFlow 2.0 is still working under the scenes, but they have almost shipped the whole neural network class to Keras. Earlier, Keras was like a third-party tool, so you could use Keras if you wanted to, but you could also design the whole neural network in TensorFlow. Now they have kind of come up with this idea that Keras can do almost all of the stuff for neural network that we want to. Let's keep TensorFlow 2.0 or TensorFlow as the framework only. So what it means is, and let me explain what it really has the implication for. So at the core of everything, let's say, it is TensorFlow itself. Okay. Now what Keras does, Keras is more of an API. Keras is more of a message passer. It mostly passes the messages. It can only do very few manipulations by itself. So now Keras can deal with data, but the point is, so you can provide even Numpy data if you wanted to. Okay, or Python types as well are totally supported. But what it does is it just does a message passing. So it takes your data and passes that to TensorFlow. Now TensorFlow will do the actual computation. So all the heavy lifting is done by TensorFlow, computation or data manipulation as well. And that will get transferred to Keras. Again, whatever the return is, so the return would go to Keras, and it would feel like that Keras has done all the computation, but it's not true. Keras is just a wrapper around TensorFlow. It's more of an API. Actual work is still done by TensorFlow. Now, what they have done is earlier we could look inside and we could also design our whole TensorFlow code. Still, it is totally possible. But they have made the whole production like that you can write the whole code in Keras. Everything will run under the hood and you will not realize it is TensorFlow. And you can interface just with Keras and everything is normal. So from TensorFlow 2.0, we are treating TensorFlow 2.0 plus Keras together always. You have to understand. They are always taken together. Now there can be like two separate sessions, although I've still tried to divide the code as much as I could, but very much it is going hand by hand, okay? Hand in hand basically all the time. So all the neural network and data manipulation even looks like it starts at Keras. Internally, it is done by TensorFlow. But for your user and purpose, you can totally code in Keras and be okay with it, okay? So there is nothing else or more you have to do right now. So this would be the design or this would be the idea on which we are going to also look for the programming. So I have kind of come up with all this new code. So I will not be mostly using the previous code. So let's look into it. Now you can find the official documentation. One second. On TensorFlow website. So a lot of examples and a lot of use cases can be found here as well. So whatever even I am covering, but you guys can also go ahead and try to cover few more. Okay. So let me check. Quick icon. Wait. So let me just terminate this one so that it could connect. Yeah, now it's connecting. Yeah, okay. So TensorFlow 2.0 is an extensive redesign of TensorFlow and Keras that takes into account over like 4 years of user feedback and technical progress. So as I might have told you, Keras, okay, so Keras came in March 2015 and TensorFlow came in November 2015. So earlier Keras would run with Theano, one of the main libraries, one of the oldest libraries. Okay, and then once TensorFlow was launched, Keras was also adopted for TensorFlow. Later Google bought Keras, I think in 2018 it happened. And then Google totally has integrated Keras into its own workflow. So it has been more than 4 years since Keras and TensorFlow has come to market, and nowadays they have been completely integrated. And few things that have been put here, which are new, or let's say you can call that they are a bit new now. TensorFlow 2.0 is built on following key ideas. It lets user run their computation eagerly like they would in Numpy. So the way you will process in Numpy, you can go line by line, right? Earlier TensorFlow was like, you will have to write some code, you will have to initialize a session, and then only you can run anything. Now with eager execution, that's not the case. Still you can maintain the graph internally, but you can go line by line execution, which makes it very Pythonic. But again, it preserves the considerable advantage of compiled graph for performance distribution and deployment. This makes TensorFlow fast, scalable, and production ready. So when you are going for production and the scalability, you still need to go with the compiled graphs idea. I will show you basically how to go with that idea. Now with Keras, it leverages high-level deep learning API, which makes TensorFlow very approachable and highly productive. And again, with Keras, you can go on a very higher level, or you can also go very low level. Okay, means you can go as close to the framework as you want, but that will require a lot of expertise. Now, some major features, as we have already discussed, are easy model building. So basically it provides multiple levels of abstraction. Okay, so basically it kind of is providing you a lot of pre-built or inbuilt functions which you can get, which you can use for your development of neural networks. Okay, and again, as I have already told you, basically you can build or develop this model at one place, and then you can put it on servers, edge devices, web. TensorFlow basically lets you train and deploy model easily, no matter what language or platform you use. And again, it provides a lot of powerful libraries and a lot of pre-built models as well. So as I was saying, it kind of provides a lot of pre-built models, so standard models, such as ragged tensor, TensorFlow portability, tensor to tensor, and BERT model, which is more of a language model. So there are like a lot of powerful models which are openly available in TensorFlow, which you can again use for your research and educational purposes, totally free of cost. Okay, so I think I have already shown you this process. So no need to do this. Again, on Colab, it is already done. Okay. So if you have not installed it, you can do pip install, upgrade TensorFlow, or if you have a graphics card, do a TensorFlow-GPU. Okay. And if you wanted to check, so first import TensorFlow STF, and then you can format, basically print out your version by tf _version _. So it will mostly tell you that your version on Colab is 2.2 RC3. Can anyone tell me what is their version on Colab, if you can run it right now? What is the version you guys can see?
Same as yours, 2.2.0 RC3.
Yes, so basically they have upgraded the version throughout collab for every user. Earlier, like if you were looking the same thing like last month in April, early April, no, not early April, actually in March, you will see it as 2.1. That was the stable version back then. Okay. Now, if you want to check that if you are running eager execution. Now, okay, so let me explain what eager execution is really. Now, TensorFlow works on this idea of graphs, okay? Anyone knows what a graph is, or less what a computational graph is? Any idea, guys?
No, Amrita.
Okay, any idea simply coming from computer science, what is graph?
Bar graph and all these graphs.
No,
like,
no, computer science,
not
computer
those.
science.
Okay, those kind of.
Trees and nodes.
Sorry, what did you say? Sorry, I couldn't hear.
It's like trees and nodes. We draw the graph. Tree-like structure.
Mm-hmm. It's not always tree-like structure, but yeah, okay. Tree is also a graph structure. So basically, the idea is nodes and edges, okay? And so these are like different pathways you might take to reach a goal. So these could be called graph. Now, what is a computational graph? Basically, computational graph kind of shows you computational graph shows you the way or kind of the order of computation. So let's say you have something called sum. Okay, sum function, let's say. And let's say you have two incoming inputs, A and B, and C is the output. So you can define as C sum A comma B, okay? And basically it will do a addition operation. Now basically TensorFlow has always run on this idea of something called static graphs. That basically you define the graph. You have to define the graph first. So you will have to define the exact order of the execution. And then once you define and once you run, it will run really fast, okay? Now the problem is it would not allow for any kind of variability. Once you put in compile time, there is no variability, okay? Whatever you have put there for execution, that is what's gonna execute. Now there was a major criticism because Python did the same thing with dynamic graphs and did it much better and they were faster. So people started giving feedbacks to TensorFlow and Google's community that basically why we are stuck with static graphs. So they came up with eager execution. Hey Dave, sorry, I'm not sure what is the problem here.
No, actually, I'm not sure whether the document which you were showing in the initial okay, I got it. The link actually I was asking the program.
Oh, okay. All right. Sorry, I did not notice that you joined late. Okay.
It's okay, thank
Anyways,
you.
don't worry. We will put in the group anyways, so don't worry about that.
Thank you
Okay.
so much.
So my point was basically, so they started looking into eager execution that you can even go line by line execution. Okay. So after a long time, especially I think in version 1.12 or something, eager execution was fully integrated. And then they kept working. Now it is from version 2, eager execution has been made default. So I cannot even run the graph algorithms. Now, if I wanted to, I can't. They have been completely shipped out. There is a way you can still internalize a graph, but it is nothing what usually used to happen before. So that's why I had to like change almost all of the code, because none of the previous code is really working with the newer versions. Okay, so checking is very easy. So the command is very simple. Basically, it is called, basically you have to just look into eager execution. Okay, so you have to look into this part. tf.compat compatibility version 1 enable eager execution. So now what it will show you is eager execution is enabled. If it is not, so basically it will run operations immediately. You could turn it off if you just want a graph based scenario, but it is more of a pain, so I try not to turn it off at any moment, but it can be turned off as well. So you can then have to go the complete graph way. Now again, if you have enabled GPUs, which I have actually already, okay, so you can also check is a GPU available or not. So you can do a simple test, tf.test is GPU available. Okay, if it is true, we will print something. And then we can also get the name of the exact physical devices which are available for processing. So let it run and let's see. Okay, so it says yes, your GPU is available, true, and these devices are physically available. Okay, so basically you can see there is a one CPU, I think it says Xeon CPU, and there is one GPU that has been provided to you. Usually standard GPU which is provided to us here is Tesla K80. Okay, NVIDIA Tesla K80. Okay, so this is the free GPU that we get provided mostly with the Google Colab. Okay, let's check the runtime comparison, that how fast. So remember there was a code, but I think it didn't run, and I told you there isn't some issue. So again, that was a graph execution and that caused the issue. So right now what we are going to do is we are going to run very much the same stuff. So I hope you remember your time module. So we will run CPU at slot 0 and similarly GPU at slot 0, because again we have a single one, so it doesn't really matter. So now you can really choose your device. So with TF device CPU at whatever the slot is, so by default slot is 0. Now you start a timer, okay? And then we do some random operations. Okay, so you generate a random normal, and then you basically do a sum. Basically you try to sum all of these numbers, and then basically you figure out how long it took time with CPU, and then you print the time. And let's do the same thing, exact same thing with the GPU as well. Now with device as GPU, let's do the exact same operations, and then finally we will try to see the GPU speed up. Now as I might have told you, the speed up, it will show you the speed up. If you run it again and again, it is kind of a dynamic load balancing that they do. Okay, so initially it might look like very simple 32x or something like that, but believe me, it is not 32x. It can very easily go beyond 50x, and you can see you start requesting it again and again. Now I'm not saying it will go till infinity or something. It maximum goes to like 90 or 100x even if I run it again and again, and it keeps on varying. Okay, because there is a dynamic load balancer that they have put over there. So it is a shared instance, so a lot of other people are also accessing this GPU at the same time. So whatever amount of quanta or time you get, you can see that you will get, and you can get like 113x as well. Okay, so it can kind of varies, but you see the amount of speed up a GPU gives over the CPU. So if you want, you can run this code and let me know how much speed up you are getting, like in multiple tries. So everyone can, if you can open my file, just give it a run. Make sure your runtime is already set to GPU, otherwise it will not run. Just execute it and let me know.
It came 133, then reduced to 85, 79, 133.
Yeah, it will keep jumping up and down.
Yeah.
But
Yeah.
you can understand getting 100x is not a big deal these days. In a free software, like in a Colab, that is completely free for us as of now, it is possible to get a 100x acceleration. So you can understand the amount of computation we have at our hand, literally free of cost. So you can see the jump that it makes, and even you can try it with more complex mathematical processes, and you will see the jump is very, now this might look like, okay, we are just doing some, but I will show you in some other operations that even doing other operations, the jump is very easily close to 80 to 90x, almost most of the time for us. So you will feel that advantage with you, and this is why we use Colab. And for our whole, like I think tutorial, Colab would suffice almost for any Colab with GPU will be more than enough. So you don't have to buy your own GPU or something. Okay. Now let's look into some basic data type that TensorFlow supports. So the very basic data type is called constant. Now what is the constant in mathematics or programming language? So it is written tf.constant. So what is the constant?
Value cannot change.
Yeah, value doesn't changes over time. Can you find an example what would be a constant?
Pi value.
Very good. Math.pi, or if you wanted to apply, I think math.e is also available. So these are treated as constants. You do not change their value. Pi value will remain 3.14 and whatever till whatever decimal spaces they have specified. Similarly, e value like what 2.718, right? So those values will remain as it is. So these are called constants. But again, you can define any number or any type as constant. So it is called the function is tf constant. Okay, and the major part is you have to provide the value, and although ideally it will kind of assign internally a data type, but you can specify the data type as well. So you can see I have a specified CS tf constant 4.0. So 4.0 is the actual value, and I have specified tf.float64. So it supports float 64 basically, which is if you think it is just a double, because float is by default 32, right? So 64 is double. And you if you want, you can do c.d type, and it will tell you it is tf of tf TensorFlow float 64. Similarly, now you can take an Numpy array, okay, and first check the values. Okay, so right now the d type is just integer 64 for this array. It is integer 64. Now remember, the problem with TensorFlow is everything has to be converted to TensorFlow tensor. So once I convert the d, which is right now of integer 64, which is the NP array, if I convert it into a TensorFlow constant, let's see what happens. Same array, d type is int 64, but the class or the object has become tf.tensor. So do you remember? I think I told you what is tensor exactly. Anyone? Tensor is just a fancy way of saying matrices. Okay, matrices on array basically. So tensor basically rank 0, and there is major two things. So tensor of rank 0. What does it signify? Anyone?
It's RE endings.
No, no. Tensor of rank 0 is just a scalar. Okay. Tensor of rank 1 is
Array.
yeah, you can think as
One dimensional, yeah.
Very good. And similarly, you can generalize this one.
2D.
Okay. And so on, so on. Okay. So tensor is just a very fancy way of saying array or matrices. Okay. Mostly people in physics and mathematics use it. So the point is basically tensor or tensor type can hold data of any dimension. That is the whole point. Okay. And if you want, you can expand the dimensions. So by default, okay. So let's say, okay. So what is the dimension here?
3.
3. Very good. So a lot of people think it is 3 into 1 immediately, but it's not. When you do this, the dimension, if you try to print it out, it should look like, okay, there's no other dimension, but ideally as in Numpy, we are trying to get it in at least 2 dimensions. So when you will expand dimensions of the B by 1, so basically what it will do is, of course, it is not going to add any extra element. Only thing is what's going to change is it will be treated as a 2D array now. So it will be treated as 3, 1. Okay. And from the shape function, you can get the shape of the tensor as well. And I hope you remember what is random normal. What does the random, so TF also has this random module. What the normal function does? It basically generates random values from a normal distribution. How? Basically, you have to give the shape. You have to provide the mean value and the standard error. Okay. Based on that, it will generate the random values. And most of the values will be from where to where?
Between -1 and 1.
Depends. Again, you have to ask me the confidence. Basically, you cannot answer this directly. But yeah, if you were to talk about the 68.4%, the first standard deviation only, then most values are from -1 to 1. But what if you can also think as -2 to 2 and 95% values will be from that range. Okay. So you can take any range. I personally prefer taking -2 to 2. So that we get bigger range and we kind of cover like 95%. Of course, all of the values, the total length or the total values could be from negative infinity till positive infinity. Why?
One question, this line number 11, right? TF dot constant was 3-dimensional, right?
Huh? What?
Like line number 11,
How
this
is it 3-dimensional?
3D, no?
How? Where did you get that idea? That's not a specification. Those are 3 are the numbers which just became a constant, TF constant.
So this is just a list, 101.
Yes, you can see the bracket, right?
Okay.
You can see the square bracket. So that
Okay,
is
and we expanded the dimension by 1 means it became 2D array.
yes, now it will be treated as 2D array. It will have a
Okay.
row as well as a column now.
Okay.
Earlier it can be only treated as a row vector or a column vector. So as I say, vector means 1D array. Now we are treating it as an array, basically 2D basically.
Okay.
For matrix multiplication, it is better to treat it as 2D as well. Okay. And similarly, what is the random uniform? Basically, it will pull out random values from a uniform distribution. That's what it means. Okay, so this is about constant. What about variable? So we have something called TF dot variable. What is that? What does variable means?
Which can change.
Yes. which can change over the execution of code. So you can define like a is equal to 5, and based on your execution of code, a can keep changing its value. Okay. So can you explain me what is going on here?
So you are generating random values between 1 to 5 with the
What's it?
is-
1 to 5, are you sure?
Between 0 and 1.
Yeah, now what are you
No,
saying?
no.
It's a normal distribution, guys. Come on.
Normal distribution, right?
So 0 is what?
S-
Okay.
Mean.
So between
mean of 0 and standard deviation of 1, but you are
Using,
generating.
using, you should say like this. So the idea is basically this is the shape, okay? Get it? This 1, 5 is the shape, and based on your standard, so basically you are pulling random values where mu is 0 and standard dev is 1, not between mu and standard dev, okay? Basically, yes, there is a range, so you can still think like most values will be from. So 95% values are here, so there's a high probability most values will be between -2 to +2, okay, or even just between -1 to +1. Yeah, and now I'm making them a variable, tf dot variable, okay, and then I'm printing the variable. The point is this var, which is a tf variable right now. If you want to check what it is, how do you check it? Okay, see tf-float 32. So it will not exactly tell you it's a variable, it will just tell you the data type, but you can see here it is a tf.variable class, okay? So basically internally it's a variable, and this variable can change its value over the execution of the code. And how do we change the code? Basically we can assign a new value, like there are multiple ways. You can directly assign a new value, or you can assign add, which can increment the value, or assign dot underscore sub, which will decrease the value. So let's take another one. Okay, and let's say I do a new value tf.random. Okay, so this is the initial value. Okay, you can see the array. So I come up with new values, and what I do is a.assign new value, and I'm trying to print and assert. So sorry. So rather than directly jumping over there, what if I just wanted to do print a? See what happened?
New values are assigned.
Yes. So basically using this assert, we are able to assign the new values here. And basically we are just matching it, of course. Assert, we are just matching it, that it matches or not. Yes, true or false. You can also add the values if you want to. So now you will have to do assign underscore add, and again if you want to see what this is, so the values have been added, and you can see the new values are presented.
If we do without assert, what will happen?
No, it's not do without assert. Assert is just checking this one, okay, that it is it true or not. See, this is where it has already happened. So if you want to add or change or add, look. So assign add is already done this one. So added values will be added to the A, whatever the previous values are. We are just checking it, okay, that it is actually different or not, or is it the same. So because there is no error, means it has passed successfully, so it is the same. I comma j is equal to new value ij plus added value of ij. So it is like manually, if I try to do it manually, just check. Means what I'm trying to say is, if you were to do it manually, number by number,
Oh, yeah. Yeah, got
okay,
it.
okay, and rather than you just do it like this, so we are in assert, we are just making sure those operations are equivalent. That's all.
Got it.
Again, you can do a host of mathematical operations. So it is equivalent of having numpy and scipy together. Okay, almost. So whatever major mathematical operations are there, it is available. And again, in TensorFlow library, you can go and check tf dot, let's say, random. Okay. So again, all the code and all the information is available. Of course, it's not possible for us to like cover all of them, but you can see that basically internally they have all the packages like tf random is available. Similarly, raw operations are available, sparse, summary, test, train, and you will see. And there is a complete module of tf.math. So if you want almost any mathematical function, which is well available in scipy as well, that is equally available in TensorFlow. So you don't have to look into any other library these days. TensorFlow math will almost cover everything. Okay. So basically, whatever you require, like power, if you require, so power is available, tf.math.power. Okay. Now let's try to first do some more simple operations. So again, these will feel like kind of Numpy tutorial. Now they have worked very hard to keep it as close to Numpy, so that might not seem much of a difference. Okay. So let's just see one by one. So let's just do a concatenation. Anyone knows what a concatenation is?
Joins to text or joins to this thing.
Yeah. So how would you concatenate two arrays or two matrices?
Usually add the elements.
Add the elements.
H stack या V stack is
Yeah. Basically, what we are talking about is either S stack or V stack. Can someone explain me how V stack works? What is the condition for V stack?
vertically added means same.
Okay.
Row wise it will add.
Sorry.
It will add by row wise. V stack.
Vertical stack will add row wise. Why are you saying the word add? I'm not getting the word. Why we are stuck with that word? It's not really adding. You understand that, right? Because look, you are dealing with numbers, so you should not say the word add. You are not dealing with strings here.
Append.
Append or okay, so append, or a better word would be actually to extend actually, but it's okay. So the idea is they both have same number of columns. Okay. Number of rows can be totally different. Okay. No problem with number of rows. This one can have 2, this one can have 3, no issues. You can do a V stack. Okay. So per column wise or per along one column, each column, you start stacking them up. So after one ends and the other starts. So it is just like concatenation. Like if I were to write like hi plus u, so it will write hi u. Okay. It is just putting things together. There is no mathematical addition operation happening. Okay. So just make sure that you are clear about this. Okay. Remember, now here we are taking a constant tensor A, which that does not change, but we are telling a variable tensor VA, which can change. Again, we are telling B, which is a constant tensor. Remember, you cannot change a constant. So try not to do a append or concatenation to a constant. That will not work. So although you can come up with a new one, which can be a variable. So AB concatenated is tf.concatenate values AB axis 1. What is axis 1?
Column.
Column. So basically the idea goes like, usually you have two axes. So this will be treated as axis 0 and this will be treated as axis 1. So this is row and these are columns. So basically it is telling along axis 1 we have to do the concatenation. So it is not V stack or S stack. Whichever axis you will tell, it will do the concatenation. Okay. So here AB concatenated.numpy, so it can show you in a numpy format. And similarly we can do a concatenate.row, concatenate rows. Okay. And what are we getting here?
Both the matrices are concatenated.
Yeah. Okay. So one is row wise, one is column wise. Okay. So remember, there is a slight difference here. This is B column. So this is actually, if you think very carefully, the first one is the actual horizontal stack. This is your horizontal stacking. This is your vertical stacking. Okay, is it clear? Zeros and ones, I guess you already know what it is. So if you just want to create a tensor full of zeros or tensor full of ones, usually there is a function like NP has zeros and NP ones. So similar TF zeros and TF ones. By default, they will be float 32 anyways, even if I have specified, but they will be float 32 anyways.
So one question, sir, because we can use NumPy also, we can get all the functions. So NumPy also supporting inside TensorFlow, right? So why always we use Tensor TF?
Because still you will have to do a conversion, right?
Okay, to tensors.
Yeah, without converting to tensors, nothing is going to work. Even in Keras, it might look like there is no conversion, but believe me, internally, Keras will convert everything to TensorFlow type.
But TensorFlow internally also support NumPy, na? Means it will support
No, reverse. You have to understand this. TensorFlow can copy the values from NumPy and convert it to TensorFlow type. Okay, it doesn't support. You have to understand there is a difference now. You cannot directly use NumPy. That's my point. It will have to be converted to TensorFlow type. Otherwise, it would not work. That's the problem with TensorFlow. It has to be converted to its own data type. Then only it will work. Yeah.
Yeah, when you are running a program, so basically when you use NumPy, right? So it's going through Keras and then.
Yeah, as when I will show you neural network code, I will make sure that you understand this part. In Keras, it will look like you can directly take an NumPy value. Yes, it's true. But what Keras is more of like an API call. That's all it is. It will pass it to TensorFlow and basically it will do the conversion in between. I will show you some is from its own GitHub. That basically internally first it converts into a TF type and then it sends to the TensorFlow for the processing. So the processing and the conversion part still has to be done. So if I can specify something in TensorFlow, if already there is a function, why would I first do NumPy and then try to convert it to TensorFlow? Because that is extra memory, right? In that time, you are using two blocks. One is for NumPy, one is for TensorFlow. Of course, the other will be delocated after a while, but still you are using extra memory. It doesn't make sense. Okay, so everything will have to be converted. Remember this part. So that is the problem actually here. And I hope you remember what is the reshape.
Yeah, it will change the shape of the array.
Yeah, so whatever you specify, but remember while reshaping, the number of objects remain the same. So you have to correctly specify the shape, otherwise the reshaping will throw an error. So here what will happen? So tensor before the reshape is like this, like a 2D array. And here tensor is like after a while, still it is like a single 1D array that has been contained. Okay, so it is in the shape of 1 cross 8. So basically 1 row, 8 columns. And you can also use a cast function. Anyone knows what a cast function is? tf.cast.
Typecasting like to
Typecasting. No, remember, there are only compatible typecasting that can work. Anyone knows what are the compatible cast typings? Which one can be converted to which?
Melt and wide, is it?
Sorry?
I mean, we used to use dcast, which is melt and wide.
Okay.
And
So basically, one thing you can always do is N2 float is like convertible. Okay, but there is a problem, of course. While you are casting something from float, if there is a value after decimals, what happens to that? If you try to do like this in 12.8, what will happen?
12.0.
Sorry?
Become 12.0.
Basically, it will become 12. There is no concept of point then. That's the whole point. In integer, there is no concept of point. And floating point only there, that makes sense. Like there would be. So basically, whatever is the decimal part, that is gone. Okay. But it is compatible. It will happen. That's my point.
Okay.
And also, you can do the string to integer of. But remember, because Unicode should match. If the Unicode is not matching, or ASCII, if you want to understand like that, then it will not happen. Okay, and here are floats, and we have just casted. But remember, basically just remove the decimal, and there is no rounding up. Okay, whatever is that integral part, that is gonna be printed out. So even if you had 2.8, it is still 2. You can't say, oh, let's integrate or round it up to 3. That is not gonna happen. It will just simply remove the floating point altogether. Okay, I hope I don't have to spend too much time here. So again, you can do some basic linear algebra operations here as well. So I hope you understand most of this stuff. If anything is not clear, just let me know. Okay, what is transpose?
Converting rows to columns.
Yeah, so basically you take any array and you convert rows to the column and column to the rows, and basically you get the transpose matrix. How does matrix multiplication works? Can someone explain me?
First row into first column, first row of the first matrix.
No. First there is a condition.
First check if columns of the first matrix matches with the rows of the second matrix.
Exactly. That is called a property called conformable. Okay. So what is conformable? That basically when you are trying to multiply two matrices, so if you have m into n and n into k, then only this matrix can be matrix multiplied, and the resulting matrix will have the shape of m into k. Okay. Okay, fine. Given they are conformable, how then how the operation works?
First row of the first matrix is multiplied with the first column of the second.
Very nice. So basically, here it is first element wise multiplication. So let's say if there is A, B, C, and we have E, F, G, then the C value. So remember, this is only this one, okay? Only the first one. And this first value is
A plus BF plus CG.
Sorry, what?
A plus BF plus CG.
CG. Okay, very good. This is just the first element here.
Yeah.
And of course, by doing this operation again and again, so first you do first row and first column. Okay, first you do one row of the column A and first column of the B, and then first row of column A with
Remaining
second,
column.
yeah, remaining column one by one. And then you shift the row of the first and you again do the same thing. So you can do a matmul, simple, it's very similar to what you do in Numpy, and that will produce a matrix multiplication in a new tensor. You can also do a simple multiply function, but remember this will be element-wise multiplication. What is the difference in element-wise multiplication?
The first element in the first row will be multiplied with the first element in the first row itself.
Yeah, it is element to element as we already said. So first the shape should be exactly the same.
Same shape, same. Yeah.
Yeah. So this, let's say A will, let's say, get multiplied by E directly, and the first element of the output would be, let's say, A or AE. Okay, and similarly element to element multiplication only. I hope you remember what is the identity matrix.
Yeah, where the diagonal elements are 1.
Yeah, so as in Numpy it is called I. It's very similar. So it will just produce an array basically where the identity matrix is, where the main diagonal is 1. Okay. Now usually technically it should not be defined, although it has allowed us for this discrepancy, but usually it should be defined only for the square columns. Okay, but a square matrices, but it allows here that you can still get the identity matrix. Okay, so it is, the function is very simple, tf.I. And here we have to use the lineage. So again, for a linear, some specific linear algebra, it has a lineage kind of module, okay, where you have a determinant. Okay, so if you want to calculate a determinant, you can use this function tf.lineage.det, which is very similar to numpy.lineage.det. And what is the dot product? Can someone tell me?
Matrix multiplication.
Sorry.
Matrix multiplication.
Yeah. So basically, both things are exactly the same here. In this case, even if you want to do a dot product or you want to do your matmul, both will result exactly in the same answer. Okay, so both things are same. So you can call your tensor dot. There is a function called tensor dot which will do the same thing, or you can do your mat multiplication, mat mul, and same results. Okay, now one of the things which needs to be in deep learning libraries is called automatic gradient or gradient differentiator or something. Why? So you require something to do automatic gradients. Why? Means this is the hallmark of any good deep learning library. If you do not have a good automatic gradient machine, it won't really work. So why we require automatic gradients?
So that y equal to mx plus c, right? Like slope needs to be 0 for the best.
Exactly.
Best fit.
Anything, yeah. Anytime when you are using a gradient descent, as the name itself says, gradient, you will have to get the gradient of the equation, or the as complex u equation is z of h of f of x. These multiple kinds of operation you are doing, you will have to get their, let's say, respective differentiation. So it's better to have the differentiation. Okay, did someone try the homeworks? So remember I gave you like two homeworks, 2.1 and 2.2. Did anyone try that? So if someone bothered to check it, mostly it was about backprop. Okay, basically gradient calculation and backprop, how to do it properly. So the backprop and the gradient descent code was already provided. You just had to write the other parts over there. So what this gradient is, and you will see very painstakingly, all of the code has to be written by hand, one by one. Means you need to know all of the functions and you need to know all of the exact equations and exact kind of derived or gradient form. Now that is not possible for us to kind of go end to end and try to find each gradient at each level. Now with automatic gradient, okay, or gradient tape as we like to call it in TensorFlow, it's like a tape which is like moving and it is just calculating gradients as we go along. Now remember, when using gradient tape from TensorFlow, you need to create a tf variable, not tf constant, because TensorFlow does not watch tf constant. And again, it makes sense, right? You cannot actually calculate gradients on constants. So it will not observe tf constants. So make sure whenever you want to calculate gradient, it needs to be a variable, not a tf constant. And remember, the great thing is you can make any gradient tape at any time and it will automatically give us the gradient. So let me show you in a very simple way how you can get it. Okay, so can someone tell me what this function is? So, okay, how do you start? You start with, let's say, two variables or two arrays for you. So let's get two normal arrays, A and B. So they will behave like inputs for us. With TF now, you have to initialize TF gradient tape as tape, let's say. So it has to be initialized as an object and it has to watch. Okay, now watch what? Okay, so now start recording the history of operation applied to it. So whatever you will do in forward pass, it will just calculate gradient in reverse pass or backward pass, which is very similar to what backpropagation does. So first you have to explain the forward operations. So let's say, can anyone tell me what is this exactly happening here? C is the equation. Just I wanted to know the equation from you.
Under root of a square plus b square.
Simple distance calculation.
Yeah.
So simply we are asking now we are asking is, okay, let's see, does someone remembers their basic maths? Now tell me what should be this value?
DC by dA, right?
Sorry.
Differentiation of C with respect to A, right?
Yeah, DC by dA, yes. See,
This is a plus b.
1 by
1 by 2.
1 by root of a square plus b square into a.
So a plus b basically.
So you have to be careful while doing this, right? This is so again, you cannot directly do this answer, right? So what you will do is, it will be a chain rule again, remember this part. Okay, so how this works? So right now, what you will get here? Can someone tell me?
So this will be half of
1 by
a square plus b square
and
upon dA.
Come on, guys, like
2a.
Okay, into 2a, right? So basically 2 and this will get cancelled and this will become something like, let me write it properly. Okay, because b will be treated as constant in the second one, so it doesn't matter. Am I right, or is there any problem is there? Okay, so this should be your final answer. Now again, this is an equation, of course, but if you just wanted to get the gradient at every step, or whenever you want to get with DC dA, so basically you want to just get the gradient of C with A. Okay, so for the tensor, these are the values you will get. So these values have been obtained how? By putting a value. Now, of course, putting all the values together and doing all of this will be very hard if you have to do by hand. So it is better to get the tape dot gradient C respect to A. C is the actual array, and with respect to A you want to get, okay? DC upon DA. You have to understand and interpret it like that. Okay, DC underscore DA means DC by DA, let's say, and print DC underscore DA, and this will be the differential form or the first order gradient. Okay, when you are taking a differentiation of C with C against A. And all of this is done automatically. So this makes our life very easy. And again, you can try to do it again and again. You can take a different variable. Miss, I'm just trying to show you a different way of doing the same thing. Even if you do not do this tape.watch A, that's fine, okay? It doesn't have to watch all the time. You just need to identify it as a variable, and it will identify what it has to do. And again, you can do the same thing and you will get the exact same answer. You can match both of the answers. Both of the answers are still going to remain same. So once you have not specified that it is a variable or not, it is better to do a watch A, but still make sure it is not a constant. Otherwise, specify it as a variable, and then you don't have to do this tape.watch A. It will automatically calculate it. Not just that, it can run in a nested way. Why? What does I mean by that? And this is why nested matters, right? Because fundamentally you are going to deal with neural networks right now. So in neural networks, what happens is there is one processing. So like there is one function and then there is another function. So when you try to do a DX, you have to understand there is a nesting of function. There is just not one function applied. So you have to differentiate function by function. Now I hope you remember how to handle this problem. How to handle this one. Okay, let me give the first simpler example. Okay, what if you wanted to do double differential? Forget this chain rule thing. Okay, let's try to do a double differential. So you have some function of x. Okay, so if you really think about it, what this really is. F of x is what? F dash x is what? This is what you are saying. So basically you can think it is running gradient on gradient, something like acceleration. What is acceleration exactly?
Change in velocity by time.
Yes. Acceleration is rate of change of velocity. And velocity itself is?
Distance.
Displacement.
Change of.
Rate of change of displacement. It's important to say displacement, okay, because it's a vector. So I can also say acceleration A is nothing but ds by dt. No, sorry, it's not exactly correct, sorry. If you were to differentiate the displacement twice, you will get acceleration. If you were to take a gradient of displacement once, it is a velocity, okay? So double differential is called acceleration. So basically you can, if you think about it, you can achieve the same thing with two gradient tips. One is outer tape, one is the inner tape. Again, C is as it is. So this is, let's say, distance. And then you do dc by dA. And then you do d2c by dA2, which is equivalent to doing it twice. So basically this is what we are saying. So whatever the outer tape gradient is, you just take one more gradient. Okay. and then you can print the final value out. Is it clear what happened?
Yes.
So you can think that basically this one is, or this part is velocity, because look, this is what? Distance over displacement. And this part is acceleration. So you can just do this, almost all of this normal integration, differentiation, whatever you want here. And just to show you almost like one of the last examples. Now you can also do it for hyperbolic tan functions, because these would be behaving like activation functions, right? So let's say you have a tan h function. So you can also get a derivative of tan h function. And this is why we use activation functions which are end-to-end differentiable. Because at the end of the day, I'm going to run an automatic gradient tape most probably, and I will try to get the gradient value. Okay. So this is the simple way of writing tan h here. Okay, so you pass the x value and we will return tf dot tan hx. Okay, clear? Then we will write another function, let's say to get the gradient. So with tf gradient as gt, y is equal to activation function, and you just want to get the gradient value, that is gt dot gradient xy, which I just want to convert to numpy. And let's return the gradient value. And let's say if you pass a value, it will tell you the gradient, or you can pass an array here as well. Okay, and it will tell you the exact gradient over there. So it's a simple operation. So if you, let's say, push 0.75, so it will tell the value is 0.5965. So let's say, let's put something heavy, 0.9, and it will tell you the gradient there, 0.4861. Let's take something very close to 0. And you will see the gradient would be slightly higher here. Why is taking so much time this time? Yeah, so you will see the gradient is much faster, because around 0 it is almost close to 1. Okay, and again you can take some negative values, because again tan h is defined for negative values as well. Okay, now there is a homework for you here. Okay, so what I have done is, so this is a simple example of linear regression. So you have to do some linear regression. Now what I have done here is, I have given you the basic idea how to run a linear regression. So I have done all the major computation part, so that you don't, so you don't have to do all of this coding all by yourself. So basics have been done here. So you can see the input dimension has been provided and output dimension has been provided. So you have to take input dimensions, means x1 and x2. Output dimension is y. Learning rate alpha has been provided, which you can tinker, subject to change. So you can change this value as you want. Now W is your weight matrix, so this is your theta basically. So basically these are your feature, these are your parameters. Equal to theta. Okay, and then you have your bias, or as we like to call intercept. Okay. Now first, this is, can anyone tell me what is this step? So this is your hypothesis. Why?
You are doing matrix multiplication.
Yes, and then adding into features in W.
Adding intercept.
Yes, so that's just a linear hypothesis if you think about it. What is this step? Now we will have to come with the loss function. So I define the MSE. So in regression, linear regression, we tend to use mean squared error as our loss function. Then what do we have to do to solve the problem?
80-20.
No, that is the part you will do. So that we make sure that you know your machine learning, training and updating through. Sorry. So GD means gradient descent. How would that work? Can anyone tell me? So basically, you will run the automatic tape. You will first compute the prediction. So this is y pred. Sorry, let me write it properly. Or y hat. Anyway, you like to think. Okay. And this is your loss computation. So this is your error. Or basically, this is the loss returned. Now, basically, this is where you get the gradient. Fundamentally, again, tape dot gradient is just gonna do the same thing. So basically, you have to get the gradient twice. Loss with respect to W first, and the other one loss respect to B. Gradient with WRT. With respect to features W and B. Okay. And then basically you assign or reassign the values. So you reassign weights. Similarly, you reassign bias or intercept, any way you like to think. And this will finally return the loss. Now your point is to, one sec, yeah. So your homework is very simple. Now by using the above one, let's say if I execute this, you will see there is no error. So it will run if you know how to make it run, okay? So basically you need to just use the function and, one sec. To generate data and utilize the above code to run a simple linear regression. Remember, everything has been done. You just have to generate your data properly in the correct format. You have to split it out. You have to run this and then maybe just test it out. Okay, this is simple work I am giving you. Maybe you have to write some more functions for maybe write function for predict. Predict might has to be done by you. Write AR2 score metric. Okay. So you have to just do some basic work, and it should not take more than 7 or 8 lines. But if you understood how the previous code is working, this would be really easy for you to make it work. Okay.
One question.
Sure.
In our basic Python version of linear regression, we did some tolerance also, right? I mean,
it's totally up to you. Yeah, miss, I have not done it, but again, you can change the code. I'm not saying that it has to be exactly the same. Again, most of my code is just to give you like a basic idea how things work. Again, I hope you are good programmers and you know how to change the code as well. Okay, so of course you are totally free to make good changes here. Okay, so because look, see, this is just the main steps, but this is not a loop. You have to understand this. So you can write the loop here, and let's say write a loop and put stop when tolerance condition is met. Fine. So you guys can do changes if you want to, but I don't think so. In train on batch or training of step, I require rather than writing train on batch, I should just write train. Okay, that's all it is. It's just a train step. So this much is being done here, but again, it has to be done in loop, right? Again and again, it needs to happen. So you need to write a loop and you need to stop when tolerance condition is met. You can do it. I don't think so. That should be any issue. So maybe I can give you a tall value right now. 1e to the power minus 3, right? So there is a tolerance value now. Do whatever you want to. Okay, so it's up to you. You can solve the problem.
Okay.
Okay. All right. Final thing, just one more thing, and maybe we can have a break afterwards. Okay, guys. Now, of course, you can do everything as I showed you, or you can define something as a TF function, or basically this will define it as a graph. Believe me, all the steps are really the same. There is literally no difference. Okay, there is literally no difference. The only thing is we need to put a TF function decorator on it. That's all. Now this makes it a graph. Okay, this makes it a computational. Now the moment you do it, now it's no more eager execution. Now what happens is, even it is no more eager execution, when it runs really fast because the structure has been well defined. So if I were to run the same thing, and if I wanted to compare both of the codes, which I will just do it. So this is dummy code without the data, of course, it will throw errors. Okay, let me show you what will happen. Let's see how fast you can take it. So there is an operation called convolution. Right now you don't need to understand how convolution works. Just remember it is a compute intensive process. So what I will do is I will create two ways of doing convolution. One is by doing TF function, okay, which will make it a graph, okay. This is the image. So I am providing an image here. And I can also do it directly, okay, where I will just call the function. And now I'm just going to do it internally in a simple way. Basically, I will just run a lambda function. So, okay, remember, the convolution function is the graph. So this one is the graph implementation. This is like TensorFlow layer. This is directly layer. There is no graph. It is executing as it comes by. And we are just trying to calculate the difference. So if I were to run this code, so it will take its own time and it will run. Okay, now see, without TF function, okay, without TF function, without converting to graph, the time is 0.00464961. Okay, and with TF function, there is a small speed up, 0.0395. So you might think this is like a very small speed up, right? Because the difference is so minimal, right? Although one thing will still happen, that if I do it again and again, you will see there might be a more or less of some speed up. Still, someone can say, okay, the difference is not too much, right? So you are totally correct. But what if I had to do billions of calculations, which is very normal for a neural network? That's not even a big deal. So if I had to do billions of calculations, you have any idea how much fast it can go? What in milliseconds, or in it is, let's say in milliseconds, you see a very small difference, and it might look like a small difference, but just think there are billions of calculations happening in a standard neural network while training the model. This could mean a massive advantage if you use @TF function, okay, the decorator. So when you are writing code for production, you should do @TF function. You should not directly write these things, because then it will be much slower. Even while running the eager execution, it might feel like it is doing its trick, but believe me, it is much slower. In the production code, it is a very normal thing to write this one, because it actually accelerates your overall learning and overall execution process. Okay, so this was the basic intro to TensorFlow type. Okay, now we are going to learn how to make neural networks. Okay, so now what is Keras really? Okay, so maybe the Keras original website is still up, so let me just show you. Okay, so originally it was run as like kind of like a front-end support or like a API support for Theano. Now Theano is dead, like Theano development has stopped long time back. Now it still runs on top of TensorFlow and CNTK, and because Google has bought Keras, so it has been completely integrated with, as you can see, with TensorFlow. So it is behaving like a Python API for deep learning, and again it has something kind of for every user. So if you are an engineer, Keras provides you with reusable blocks such as layers, metrics, training loops to support common use cases. And for most of you, it will be more than enough, to be very honest. As a researcher, you might not like it, so you can write your custom layers and metrics as well. So that is also equally possible that you can write your custom layers, metrics, laws, and everything. And similarly, because you can try to develop different libraries. So TensorFlow is a very large ecosystem. Okay, it's a framework. And it has so many different libraries and they should be able to talk to each other and kind of share components, and they require an API standard. And basically that is what Keras is here to provide. Okay. Now fundamentally, let me explain. Again, the idea remains very same, but just to revise neural networks, just to make sure that you remember everything. Now there are specific kinds of networks and layers as well, but let's start with the fully connected and the sequential ideas. So this one, okay, so this will be referred as your node or artificial neuron. And the whole thing is called layer. Okay. So the one of the basic classes in Keras is no surprisingly called layers or base layer class. Okay. Basically, this is the first class you need to understand, and Keras literally derives everything from it. So a layer encapsulates a state or weights and some computation defined in the call method. Okay. So again, what is artificial neuron and what does it does? Sharing this link with you guys as well right now. Yeah. So what it does exactly? One artificial neuron.
It acts as a perceptron.
So what is the point of perceptron? Like what perceptron does really? That's my question.
Based on weights, it will basically dot product with the input and then use some activation function to give the output.
It's a simple idea. Yes, there is a weight. There might be incoming input. So Wi transpose, and then with some activation function, let's call it a sigmoid, you can do the activation. So that's the idea, right? A layer encapsulated state, weights, and some computation, which is defined in the call method. That over there you define how the computation will work. That's all it is, right? And this is why like most of the stuff from Keras will come from the base layer of this layer, okay? Base layer class. So let's start with this. So again, you have to import TensorFlow because a lot of time you will have to handle data from TensorFlow. Now, what I'm trying to do in the very first one to show you a very basic way. I can take a very smart approach as well, but then you might not be able to understand immediately like what just happened here. Okay, so see from TensorFlow.keras.layers. Now everything is within TensorFlow. Earlier Keras was a very much a separate library. You import something called layer. Now here I can go and define my own layer if I want to. So I am showing you a way to define your linear layer. What it does is wx plus b. That's all it does. There is no other different computation. So again, if you want to think in terms of linear regression itself, this layer could be useful, right? You could create a linear layer and solve the problem, right? So I come up with a constructor. So I have to come up with two things, constructor and a call. So constructor will, okay, what is a constructor? Does anyone knows?
Initialize the memory value.
Yeah, basically it initializes. The idea is whenever you will call this layer or linear, it will be initialized with some stuff automatically. So what do we require to initialize? Okay, for weights, I will require random normal initialization. Okay. Then what about variables? So let's say, how do I do this? So w init t random normal initializer. Again, as you might have asked the question before, you could start with numpy, but believe me, the problem is fundamentally it has to be converted to TensorFlow type itself. And then you initialize this variable and basically you provide it to be true. Okay, so it has to be made trainable. Trainable means the weights will change as the steps of training will go forward. You can initialize some basic floating type, and you can do the same thing for b as well. Okay, so b has been initialized as zeros. Okay, for b you can initialize with some constant like 0, 1 or some constant that you choose. There is no hard restriction, but usually we should have some random normal initialization for the weights. Okay, it converges faster. Okay, now call is the point where the mathematical function is defined. So can you tell me what is happening here? Anyone?
Wx plus b.
Yeah, that's it. Input into W, mat multiplication will take care of the transpose internally, plus B. So this is where the computation is defined. And you can instantiate your layer. So now by default, unit is 32. What does unit means and what does input dimension means? This is number of artificial neurons, right? And this is
Input feature.
input features. Very nice. Remember, these are default values, but at the time of initialization, you can define your own values. So based here, how many nodes are there?
4.
4. And input features are?
2.
Very good. So the point is, if I would have if I would not have specified anything, then what would have been the number of nodes?
32.
Yes, then the default value will take over. It's the same like function. And the input dimension will also be 32. Okay, so let's say you have specified it. Okay, so let's call this. So you can start with it. So here what we are doing is we are starting with linear layers and we are passing values 2, 2. Basically it is all ones. That is the y. Okay, and weights are automatically tracked here. So once you start, you can assert linear weights is equal to weights, linear w and linear b. Now rather than doing this, now again remember this is dummy code. Without the input data it will not work because there is no shape value I have provided right now. But you could initialize rather than doing all that drama that we did over there. Although this is not the way I will prefer. I would still prefer the previous way where we did determine our own. But if it is some common function that we are using, we can directly initialize everything. Okay, and we can do this self w tf variable initial value where you have to provide the shape and float 32. Okay. Because shape is not provided, it threw an error because it's a dummy code. Okay. Or usually much shorter way is you can add weights with the shape and the initializer random normal. So you can see as we are going, we are getting a higher level of abstraction. Look, one can go and create everything on their own as well. That is let's say if I wanted to create a different layer with different kind of computation which is not supported by Keras by default, I can create my own layer like linear I have created, let's say. But as you can go forward, you can realize there are a lot of code which is just reusable. Initializing weights with random normal is not a very big new thing. Okay, so typically I can just do this and that will take care of everything. Okay, initialize a random normal shape, just provide the shape and those many weights are just added over there. And this is the whole point I'm trying to make, that basically in various ways I can implement literally the same stuff that I've shown you here. Same thing can be written as this as well, what I showed you already. Same linear class can be built in a very different way, accordingly the way we require, and it's the same idea. It's not very different. Anything you do is not here a problem, but you can see your levels of abstraction based on your use case can change in Keras completely.
This add underscore weight is a inbuilt function, right?
Yes, exactly.
But it is not
And
tf dot add underscore weight, right?
no. So Keras has its own functions. So
Okay.
right now we are working at a Keras level. I hope you understand this. So see,
Yes.
the base call is from where? TensorFlow.keras.layers. So this is the base class, okay, from where everything is being taken. So internally now Keras will take care of everything, okay?
Okay.
All right. So yes, Keras has its own functions which can take care of this part. Okay, so weights created by layers can be either trainable or non-trainable. Mostly it has to be trainable, okay, otherwise there is really no point. Okay, but you can if you want to, okay. So you can have a class of, let's say, compute sum. Let's say the layers purpose is to just compute the sum. That's all it does, let's say. Okay, so you can create trainable false. Okay, there's the flag has to set to false. Then these are non-trainable weights. Okay, so in the process where you are trying to update the weights through gradient descent, it will not happen. It will remain as it is. Okay, although I do not specify or I am not proposing that you guys start doing this kind of stuff. Just showing you a way like it is totally possible to do it. So what am I doing here is, okay, can anyone tell me what is happening here? So fundamentally, whatever the input value has been provided to you, you are getting some of that. And whatever the value has come, you are just assigning add, means you are adding to that value. That's all. Okay. And when you try to get a sum, what will come? Okay, so let's say you come up with a compute sum. So remember, the purpose of this one is to compute sum. Okay, that's all. So tf dot wants to do. Okay, so if you want to get my sum x, so what would be the value? Compute sum is 2 and x is this. Okay, so my sum, if I wanted to get passing x as the value, what would I get?
2, 2.
Yeah, you will just get 2, 2. Similarly, and of course, I'm just converting into a Numpy format so that I do not see TensorFlow. And if I were to do it once again, then if you have to do it once again, then what will happen?
4, 4,
Yeah,
4.
2 plus 2, 2 plus 2, it will be 4, right? And you can see the trainable weights and everything, and you can check this out that this is how the weights are changing. Not the weights are changing, you are directly asserting there, okay? No, trainable weights are not, non-trainable weights are not of much use. It is just one of the terms that I wanted to explain. Fundamentally, we are going to use trainable weights because we want to use it for neural networks. We don't want to use it for addition purposes in life, okay? So now, how to compose layers? Okay, this is where things get really interesting. Okay. Now, you can come with linear models or systems which could be layer after layer, right? So you could have different linear models. Let's say linear 1, linear 2, linear 3. So rather than just thinking about one layer, I can also think about a stack or let's call it a stack. Simple stack of linear layers where I can come up with linear layers where 32 is the number of nodes. Here also the 32 is the number of nodes, and here it is 10. and I am utilizing a function called relu. Okay, what is relu? So guys, I hope you remember there are activation functions.
Rectified linear unit.
Yeah. So few of the activation functions like you might already know are sigmoid, tanh, and what else you know? There is something called ELU as well, exponential linear unit. There is also called LU, which is linear unit. Okay. Then there is something called ReLU.
Softmax.
Sorry, softmax. Yes, softmax is there. ReLU is there. Okay. So what is ReLU? It is called rectified linear unit. What it really means is, given your x and y coordinate system, in the zero term, or sorry, in the negative space, it is touching this 0, and in the positive space what happens? It is x is equal to y, exactly at 45 degrees. So this curve is called a ReLU activation. Okay. So now in call I have to define the whole computation using all the layers. Okay. So how will this layer by layer thing will go? So fundamentally it doesn't have to do anything, it just has to apply the ReLU function. So what it will do is it will take the input first. Okay. Now that's x, and then you will apply tf.nn. NN is a neural network class where ReLU is provided. X, and similarly you will pass this value to next linear value, next linear layer, and that will again pass it to the ReLU, and that will return, let's say, the final layer, linear layer 3, okay, with x. Okay. So till it is positive, it will be just behaving like a linear layer itself. If it is going to be 0 or negative, it will just be put to 0 immediately. So it will look like it is all positive linear class itself. And then you can call the MLP. So when you will call the MLP, it will be initialized with the default values. Now again, in MLP, you can call and you can provide the shape, input shape, and then you can weights are recursively tracked. So weight will be tracked. So you can check the weights as well, that MLP.weights, how many weights are there available. Okay, so once you look in this one, so okay, what do you think about this one? What is this TF1's shape 364? Anyone?
Three rows, 64 columns, all are ones.
All are ones. And what is the purpose?
I think we are starting with weights equal to 1.
Because linear 1 and linear 2 are 32.
32, yes.
32.
And
Which adds up to 60.
anyone? Okay, so people didn't exactly get this idea. Okay, let me help you out. Okay, guys, remember what are these? These are constructor initialization. Okay, but only when you have not provided anything yet. Then If you provide your own shape, then what will happen? So basically it has become like linear 64, linear 64 and linear 64 three times. Get the idea what just happened? This is a constructor initialization. If I would not have provided anything internally, then this shape would be taken. Understand that this is the important difference. If I provide a shape or if I tell you how it is, then that's how it will be initialized. That is the difference between, okay, that is the purpose of constructor, right? What is the constructor? In any programming language, what is the constructor really? If anyone has taken ever see anything, one of the most simple definitions our teachers or professors tell is it allocates the memory and initializes values provided by user / default values. If user has not provided something, then default values take over. But remember, if user has provided, then the memory space will be initialized by the user's value, not by default value. This is the difference, and you have to remember this part. Okay, so if they are not available, I can initialize the way I want or I deem fit. Okay, now this was about like creating your own layers, and I showed you there are different ways. But the point of using a library is I don't have to. Almost all the major layers or all the major types of neural network layers are well available here. So I don't have to go ahead and write all the layers. And as your study with neural networks will go forward, you will see you will be using a lot of these layers. You will realize you don't have to use or build your own layers. These have been already internally built. You just need to know how to call these layers. Okay. And there is a link of there is a link for this. So there is a complete module called tf.keras.layers where you can go and see how many kinds of layers are already available. So it's very rare, it's a very rare scenario that is going to happen that you will have to write your own layer. Okay, and there's a base class layer here as you can see, and through this one you can create your own layer. But almost everything that you might ever require is well available here. So first of all, rather than starting to write your own layer all the time, maybe just look here and there's a high chance you will find these layers, and there are some experimental layers as well for pre-processing and these things, but I have not used them. Okay, so as you can see, almost for all the major tasks, although I know you might not know all the major tasks, how to do things, but you can see a lot of mathematical functions are already provided here. And you should first think about using these layers rather than jumping directly to create your own layers, because that will take a lot of time. Okay. Now let me explain the purpose, how things work here. Let's say you come up with the basic layer. Okay, you implement or you start with layer, but then you can add layer as well. You can add layers. Okay, here your add layer could be, and I will specify how to add layers exactly. Then once you have add layer, you will have to tell the way to compile it. Now what is a compile is, compile contains the rules. Okay, it will ask you what kind of optimizer to use. Okay, what kind of loss function to choose. Okay, basically it will ask you the rules of running the network. Is how the network will really train, like what kind of optimizer, what kind of loss function, what kind of metrics to use. Once you have provided the compile, then there is something called fit function, which is exactly the similar, exactly same as what you have used in scikit-learn. You have to provide your train X and train Y. There are some other flags. You might have an option of batch as well, that how much batch size you can provide. Then you will have predict function as well. And if I remember correctly, there is something called score function as well. So the rules are simple. First, to define your layers, which will generate an architecture. Compile will give rules to run the network. Then fit will take care of the training part. Prediction, this is as it will take care of prediction. And here you can get the accuracy or some metrics that you choose with the score function. So these are the 5 major things that's going to happen in most of the Keras code. First, we will kind of make an architecture, then we will compile, then we will fit, predict, score, and of course there is data pre-processing and everything. But right now that's not our major concern.
Optimizer is like gradient descent.
Yeah,
Right?
gradient means there are much better ways of than gradient descent. So till like logistic regression, basic gradient descent is more than enough for most people. But in neural networks, and I will explain you later, that is not. There you require a lot of things. Okay, because I have not right now, I just see the problem that because I have not explained you dropout, it might be slightly tricky to explain this. So right now I will skip this. Okay, I will explain you in a different example because I just realized I have not explained you dropout at all. Okay, let's take a functional approach. How to do this? Okay, so now Kera again. Sorry, this will again throw an error. Yes, because I have not called all of this, but I will show you. Don't worry. Okay, so now Keras has already functions for almost everything that you can think about. Okay, it has for input already. Then even for linear, it has already this. For dropout, there is already a function. So you can define them step by step. That linear will take 32 and it would take inputs. And dropout will take x. So you will take the values from x. And again, the output would be a linear layer with 10 nodes with x. Okay. But there could be a better way where you specify things as model. And this is what most people use. You specify things as model, and under this model, you keep adding stuff. You keep adding layers. Okay. So let me show you how to use this model idea. Okay. So this is what I'm talking about. Now we are gonna do some kind of subclassing. So what you can do is, okay, one of the major classes of, or let's call it only one class that really interests is sequential. Now what is sequential? Sequential is layer by layer in order. What it means is first data will move in layer 1, that will move in layer 2, layer 1, layer 2. Let's say then you have output layer. So this is how data is going to move. And similarly, if the backprop is going to happen again, it will happen sequentially, of course. Means of course the parallelization part is there. But this sequential is first layer 1, layer 2, then output, and whatever the layer wise is. So whatever order you provide here. Let's say you import TensorFlow Keras, import sequential. Sequential is a functional API. So you can call your model a sequential model, and here you just provide step by step. So the first layer would be linear. Okay, so sequential model, the first is linear layer with 32 nodes. Okay, what is the next layer? A dropout layer with 0.5 probability. So means 50% will be dropped. And then a linear layer again with only 10 nodes. So this is how your network starts to look like. Now you see, this is the easy way of defining things. And for most purposes, for most general purpose, you will also get very much used to using this point. Okay, this is how you are going to use this. So basically the idea is fundamentally, in long run what you will do is, and the way I also do it, so you have double O models, which is object oriented. So you can create your classes and objects and everything. or you can directly start calling functions. So people who are not fan of object oriented or who have not taken like classes on objects in very depth, they don't like object oriented, like what I previously was doing. Okay, that defining everything and writing everything and try to define constructor and everything. So people have a good way that they can just call the function directly with a parameter, that function and parameter that you all have to do, and it will work. Simple. So rather than like writing our own constructors and calling all the giving it the call function and everything, you can just introduce the functions or the layers as it is, just pass the parameters and be done with it. Okay, so even in my coding, I have found that a mix of object-oriented and functional kind of produces the best result, but it is very much up to you that how to do this. Now, similarly, that the way you have layers, you also have something called losses. Keras.losses like battery cross entropy, right? So you can run and you can get a loss over there if you want to. Okay, so you can see that based on binary cross entropy, it has tried to figure out a loss by simply comparing y true and y prediction, and that comes to 11.522. Okay, of course you can change it to MSE and everything, and accordingly you will have to change the target and prediction. And you can do this for categorical cross entropy, binary cross entropy, KL divergence, MSE, MAE. So there's again a whole class of losses in Keras already, which you can leverage. So again, you don't have to write literally anything here. You just need to understand how to make it work. Binary cross entropy, categorical. There is hinge, KLD divergence, and there is MAE, MAP, mean absolute error, mean absolute percentage error, mean squared error. So you just need to call them. There is a Poisson, then reduction, serialize, parse categorical curve, and squared hinge. So these kind of loss functions are already provided, which you can use. So, and similarly, I have tried to kind of use a simple accuracy function. So again, it also has something called metrics. What is metrics? What are metrics?
Like R1, F1 score, R2 score.
Yes, exactly. So again, Keras has a rich class of metrics, and again, same way, you can just look it up. And this is the advantage of using, so you can go here, and rather than actually going into metric, you can look, there are so many metrics already available, so you don't have to do practically anything. You just need to know again which one to call. You have true negatives, true positives, precision, recall. You would not have F1 score exactly as I remember. Okay, so yeah, there is no F1 score if you look very carefully, but because you have precision and recall, you can very easily calculate F1 scores. But it has accuracy, AUC, binary accuracy, binary cross entropy, and everything, cosine similarity as well. So you can utilize that. Cosine similarity, you might have looked into NLP. Have you checked cosine similarity yet?
Yes, yes.
Yeah, so in NLP, actually, when you are comparing two texts, cosine similarity is something that people look at. And you can come up with, again, accuracy terms, and you can try to get accuracy values, or you can come up with precision, recall, and everything. And you can see, like in this case, we are getting literally just 0.5, okay? And again, just taking an object-oriented approach, although this is not something I want you to do. But if you wanted to write your own F1 score, you could very easily write, but there are certain update steps. So first you have to initialize, then you have to put an update step, okay? How to update and how to kind of pass the values, and then how to pass the result values, okay? It's not advisable for everyone unless you are really looking into how to exactly define your own metrics, but not something I would really like you guys to go in very in deep with, because this is not really the topic I want you to focus right now.